This is the third segment for the week of Martin Luther King Day holiday. I want to talk about the equivalence of ANOVA and regression. And I also want to talk about the use of dummy variables to investigate functional form. So let me start out with a screen share. So why don't you pause? Okay. This is a PowerPoint that's available on the Canvas syllabus. And I just want to go through what you probably suspect, and that is that a regression approach is exactly the same thing as an ANOVA approach. So let us be able to advance our slides. So this was the table that you answered questions about for the assignment for this week. And I think most of you understood that if you have a simple regression, in this case with fall kindergarten math scores regressed on a bunch of dummy variables representing race, ethnicity, that you have to select an omitted group. In this case, the omitted group is whites. And then the coefficients on the included groups show deviations in this case, a standardized math test between whites and these various groups. A nice thing about the Fryer and Levitt article, if you look down to this highlighted area, I always like tables where the notes to the table and the table itself combine to be completely self-explanatory. Here you've got case counts, you've got R square, and you have this explanation that the dependent variable is a math test score, their IRT scores normalized, and so forth. And then it points out that non-Hispanic whites are the omitted race group, so all the coefficients are relative to that group. All right. So even if, I think a lot of people, when they write articles, think that readers are going to read every single word of the article. That's a little bit naive, and people kind of drift through empirical articles and go right to the tables and start to try to understand the tables. So you don't want to reward that behavior too much, but as a favor to those people, you want to make these tables as self-explanatory as possible. And that's indeed what Fryer and Levitt have done. So let's come close to reproducing that regression. They use the ECLSK, the class data set is the ECLSK. Paul was able to come pretty close to replicating the sample, not quite exact. There were a few subtle things about imputation that they engaged in that led them to have a few more observations. But this is essentially the same regression. And you have these coefficients that are almost the same as what is in the article. And we want to compare what you get out of this regression with what you get with a one-way analysis of variance. All right, so here's the command, one-way, same variable, we're limiting it to the same sample, so you get exactly the same case count. And we want to see if, in fact, the two approaches are giving you similar kinds of information. So here we have a side-by-side comparison. On the left is the regression. On the right is the analysis of variance. Analysis of variance is nice in that it's just a listing of the mean values, in this case, of kindergarten test scores across groups. So whites have 0.332, which has the interpretation because these test scores are standardized across the whole sample. That means that whites on average are about 1/3 of a standard deviation above the overall mean of the sample. And from last time, we learned that, and I think most of you understood, that if if in the regression, whites are the omitted group, and it's just a straightforward regression with no other covariates, then you ought to get a constant term that reflects the white mean, right? 0.3325539, 0.33255,388. All right, so, well, which rounds to exactly what the regression tells you. So these are the same numbers. If you look for the black coefficient, that shows the deviation between blacks and the omitted group whites, 2/3 of a standard deviation. That should be in the ANOVA a simple difference in the two means, right? So if you take those two means and get a difference, it's exactly the same. So nice thing about you know, so many things that we try to understand in education research are fuzzy. They're complicated. They're kind of convoluted. But with regression, with statistics, internally to statistics, you can have exact matches, right? And in this case, you've got the same sample. You have essentially the same procedures, regression and ANOVA. So you should be getting exactly the same results to the 8th decimal place. And in this case, that's what we're trying to show. Not quite the 8th decimal place. But this raises a larger point that I'm sure Paul will emphasize in lab, that when you're in the world of statistics, things should make sense. Things should make sense within that world of statistics, right? So once you get to know a data set and are starting to engage in an analysis of it, things should make sense. Things shouldn't be surprising. You should be able to double check things so that they're exactly the same. And that's an incredibly valuable thing to do. Think about the task of programming up data for an article. You'll want descriptive runs, you'll want correlations, you'll want all sorts of regressions perhaps in a quantitative article. The chance that you'll get all of that right are near zero the first time. So you're going to make mistakes. And the key for being a good quantitative analyst is to engage in kind of a constant series of distrustful checking to make sure that you haven't made mistakes, because you probably have, right? So Paul again will provide some examples of ways of you form a variable, new variable, you look at its properties to make sure it's formed in exactly the way that you thought. You run a couple of regressions that ought to be similar, and if they're not, then you probably made a mistake. And you know, diagnostically, if you are running regressions and all of a sudden the standard errors start to get larger, we talked about this in the previous lecture, something's wrong, something's wrong. Maybe it's the data, maybe you made a mistake, right? So you want to take advantage of this within statistics exactness to help diagnose your quantitative work to make sure that you get it exactly right. If you want external motivation, you know, I hope it's certainly the case in some disciplines like economics. Whenever you publish an article, you publish the data along with it. And anyone can come along and take the data and try to reproduce what you found in your article and then extend it to show that it's that it holds up under alternative kind of analyses. So you don't want someone to be trying to reproduce what you the results that you put in the paper and come up with different results and find a mistake that you made. So you can be internally motivated, which I hope you all are, to get it right. But you can be externally motivated because you don't want to be, you don't want your mistakes discovered in that kind of way. All right, so enough of that sermon. Let's keep going here with this comparison. Here I've highlighted in green the information about sums of squares. This are the error sum of squares and the total sum of squares down at the bottom. Those are exactly the same. Explain sum of squares, 1094, 1094. Residual or error sum of squares, exactly the same numbers, right? And if you keep going and compare the F statistics, how well did you do in explaining the differences across groups in terms of these test scores? You can look at the R square here. It's about 10% of the variance. The F of that is 288. You have exactly the same F over here. Stata doesn't give it by default, but there is kind of an R square measure, an eta square that you can get from ANOVA. So the point here is that both regression and ANOVA work from the same least squares kind of criterion and produce exactly the same information. So all right, so let's keep going here. That's when you've omitted the white group and you get this kind of equivalent. What if you omit, in this case, the African-American kids, right? So you've got white, Hispanic, Asian, and other. And then this constant, that constant should be the mean of the Black children. And if you do the same, well, in this case, we're comparing, we could have done the ANOVA, you can do it yourself, you'll find exactly the same thing. In this case, we're comparing what happens when you omit the Black category versus omitting the white category. And one of the purposes here is to show this test function that we talked about in the previous lecture. All right, so what's going on here? If you look to the left-hand regression at the Hispanic coefficient, over here, we've omitted the Black category. So the minus 0.043 is the difference between Hispanics, the included group, and Blacks, the omitted group. Well, over here, we've omitted the white category, and we've got two coefficients, one for Black and one for Hispanic. So the difference between those two coefficients ought to be identical to the Hispanic coefficient over on the left-hand side, and it is to as many decimal places as you want to take it out. Now you can, if you want to know whether Hispanics differ from whites, you can run a regression omitting Blacks and looking at the coefficient for Hispanics. Get a significance test. The t is only 1.2, so it's not p less than 0.05 or p less than 0.01. If you omit whites, it's neither of these coefficients tells you significance levels of the difference between Blacks and whites. They're both differences relative to the omitted group, which is whites. But so the question is, how do you test this difference short of redefining what the regression looks like? And that's what this test function is all about. You, in this case, you want to test the difference in coefficients with two variables that you've included in the regression. In this case, it's Black and Hispanic. So we do test that the coefficient on D Black is the same as D Hispanic, which amounts to 1 minus the other equals 0. That's kind of the null hypothesis test. And what it tells you is that the F is 1.44 and the probability level is 0.2301. 0.2301 is the same as the probability level you get over in this left-hand regression. The T isn't the same as the F, but one handy fact is that if you look at the T distribution and the F distribution, it is the case that the square of the T statistic equals the F statistic. So is that true here? Well, the T statistic is 1.2. If you square that, you get 1.44. And that's exactly what the F statistic says over here. So again, the f-tests and the t-tests are just flip sides of one another. You've got essentially the same information. You're just organizing it in a different way. So this test function, which enables you to test differences in coefficients within a regression, is very handy, and we'll talk about a number of uses for it. Any questions, Paul, channeling for the class?
None I can think of right now.
Okay. You know, next Monday, Friday, 11 to 12, I'll have kind of office hours for people who have questions, but I might also have a little bit of time at the beginning of next Monday's class to do the same thing. So that's an idea of how dummy variables can be used for looking at group differences in some outcome. And a question is, you know, if ANOVA and regression are giving you the same results, why not just stick with ANOVA? In a way, ANOVA output is clear. It just lists the mean values for all the groups you have in an analysis. You're not dealing with these deviations. There are a lot of advantages for more sophisticated analyses. One is that you can handle covariates. Of course, there's ANOVA, which handles covariates, but regression does it in a better way in a number of respects. But the main reason to stick with regression is because it enables you to do all sorts of fancy things that we'll be doing over the course of the quarter. Quadratic forms, fixed effects. We'll talk about all these things, logistic regression, these test comparison. All those things can't easily be done in ANOVA. So that's why we're using ANOVA. Regression is kind of the base procedure. And this is just to show, if you're familiar with ANOVA, that it's really just the same thing. Okay, so let's turn to a different way of using dummy variables. And that is to determine functional form. If you think back to the very first class, we were looking at the relationship between average family income, averaged over the first 15 years of children's lives, scaled in tens of thousands of dollars, and children's years completed schooling, right? And we estimated a linear function. It was a very small coefficient. We thought, well, maybe it's not linear. Maybe it's the case that the function is steeper at the beginning at lower income levels than higher income levels. We did this spline function split at $20,000, and indeed we found that the responsiveness of completed schooling to tens of thousands of dollars at very low income levels is much higher than the overall association, 1.3 instead of 0.14. And that once you get above 20,000, you gain only the difference here, which is 0.13 units of completed schooling, years of completed schooling per $10,000 of income. So that was one way to look at nonlinearity. Another way that we won't talk much about is to look at a log linear function. But the most flexible way is to look at dummy variables. So let me pause here for a second and then switch to the board. So why don't you pause, Paul? Okay. So as I said, a nice use of dummy variables is to check for functional form. By functional form, I just mean what is the relationship between two variables, right? In this case, in the poverty article, the outcome variable was children's years of schooling. The key independent variable was family income, averaged over 15 years. The functional form question is, how are these two things associated? A linear regression just assumes they're related in a linear way, but that isn't obvious from either theory or from the data. The actual data are going to be this messy scatter of points. And what you'll want to do from that scatter of points is figure out how these two variables are related, right? And you can try to draw a line. You can try to draw two lines, which is what we did with the spline function. You can try to draw a quadratic. We'll talk about that next week. In fact, if you look at the Gordon book, she has this multi-page treatment of how you go about selecting functional form between linear, log linear if you log the y variable but not the x variable, log linear if you log the x variable but not the y variable, log if you log both. And there are statistics that have been developed for choosing across different kind of functional forms. But I don't know, that seems, I've never done that. It's letting, in this case, letting statistics tell you things that you ought to be discovering in other ways, right? So what dummy variables enable you to do is to free yourself from any particular functional form. When you've got a functional form like linear, log linear, that's called a parametric model. Parametric approach. And what that means is that you're specifying a functional form and getting the parameters, a slope, a changing slope, that from that functional form. But you've got to specify what that functional form is. You could specify a bunch of different ones. What's appealing is to come up with a non-parametric approach. No assumptions. About the relationship. Let the data speak. Now, you might not want to actually feature a non-parametric approach in the main results from an article that you might write. But as a preliminary step, if you really are trying to understand what the relationship is, what the functional form is, sometimes it's useful to take this particular non-parametric approach, which is using dummy variables. That's all this is. So with the article on poverty and children's completed schooling, the dummy variable results are listed here. It's the same thing that appeared in the article. Dependent variables, years of education, and you're given coefficients on 4 different dummy variables. Whether 15-year income averages between 15,000 and 25,000, 25 to 35, 35 to 50, and 50 and above. And for each of those dummy variables, the regression is telling you the difference in completed years of schooling between all the children in that group and all the children in the omitted group. And the omitted group is everything that's not included here, which is $0 to $15,000. So that's useful. You can see relative to kids who are very low income, kids who are pretty low income, attain almost a year more completed schooling, 0.82. Standard error is 0.27, so it's a significant result. You can be confident it's not 0. And as you continue to go up the income scale, if you're $25,000 to $35,000 a year family income on average, relative to a much lower income, you complete 1.41 more years, 1.69, 2.35. All right, so what's nice about the dummy variable approach is that nothing's constraining the value of these coefficients. The data are free to say exactly what it is. And if you think about what these are telling you, suppose you've got this scatter over here. The first group is $0 to $15,000. So let's just mark 15,000, and then you've got 15 to 25,000. Then you've got 25 to 35, 35 to 50, and 50 and above. All right, so one way of thinking about what the dummy variables tell you is to think that all this is doing is finding the mean value of children's years of schooling within each of these groups. Okay, so suppose the mean value of all of these dots in the less than 15,000, let's say, is 11 years of school. We got that just by fitting a mean to that group of the 0 to 15,000. Now we're going to get the mean of the 15 to 25,000s. That's going to be close to 12. And it's close to 12 because I know that that mean is 0.82 years of education higher than the 11. If we go to the next group, 25 to 35, we're going to get a mean that's still higher, and then still higher. And then finally, I said, et cetera here, you know, the income distribution in these dollars, I'm trying to adjust for inflation. Average family income is probably around $50,000. So there are as many points out here as there are over here. I just didn't put them all in. But when you're getting this dummy variable coefficient for 50,000 plus, which is 2.35, you're averaging over all the observations to the right of 50,000. And that's going to be, you know, some number like that. So, you know, I hope whatever this base value is, this is 0.82 years more. Whatever this difference is 1.41. This difference relative to 11,000 is 1.69. And then this difference relative to 11 years of education is 2.35. All right, so I probably haven't drawn this to scale very well, but you get the idea, I hope. Now you might think this isn't a very satisfactory way of fitting a bunch of lines to data, because you're kind of throwing out, you're just fitting a horizontal line, in effect, to get the mean. Horizontal line, horizontal line, horizontal line. And there might be actual increases, systematic increases within this interval, within this interval, within this interval. And you're kind of losing that by just estimating a mean. And that's certainly the case. You're not explaining as much of the R square, or you're not getting as high R square as if you had exactly what the best fitting linear function was. But it turns out you lose almost nothing in terms of explanatory power. It's really surprising how a set of 5 or 6 dummy variables account for almost as much variance as a functional form that fits the data exactly. But the main point is not to get a high R square. It's to see how the height of these lines progress, right? Are they progressing in a linear kind of way? Are they progressing steeply at first and then in a flatter kind of way? That is the information that you want to get from this kind of dummy variable approach. And then once you have that, let's say that after looking at this, you determine that yes, there's a pretty, and this is what we did when we did the research, that there seemed to be a pretty steep increase at first, and then it tailed off. All right, where have I put the eraser? Paul, where's the eraser? Oh, on the floor. No, that's the failed part of the eraser that fell off. Here's the eraser. All right, so what we're doing is really tracing out a mean fit to less than 15. That's relatively few people have very, very low income. So the mean is probably more like 12 or 13 $1,000. So we're getting this pattern of increases. We go up like this, and then when you wonder on a scale, on an income scale, where you should put the point associated with greater than 50,000, it should be at the mean income for everyone above 50,000, which is a value of say 80,000 or something like this. So this 2.35 difference from whatever the omitted group years of education is should be way out here. And indeed, you're getting this kind of steeper slope here, flatter slope out here, functional form that these dummy variables are revealing. If you're looking across the different functional forms that we ended up presenting in the data, I think the spline functional form, where you're fitting a line segment up to 20,000, and then a separate line segment above 20,000. This was the 1.3. And then this was just 0.13. So even though we took a look at dummy variables, we ended up highlighting the spline approach because it produced not a whole bunch of numbers, but rather 2 numbers that you can explain. The easiest thing to explain, hope things are linear, because with linear is one number, the 0.14, and you can explain that in a very simple way. Dummy variable approach gives you a whole bunch of numbers, but the spline approach which seems to fit the data pretty well. That's the dummy variable approach shows that. Gives you just two numbers, and they're quite easy to understand. For low-income kids, an additional $10,000 a year for 15 years is associated with 1.3 years of additional education. For kids with incomes above $20,000, this is all back in 1995 dollars, so 20,000 is more like 30,000 now. But for middle and higher income kids, additional tens of thousands of dollars are associated with about a seventh of a year of additional education. All right, so big contrast, and that difference in slope is statistically significant. So that non-parametric look with dummy variables, you don't want to do it with all the variables that you've got. Typically, in a research article, there's one key variable that you really want to focus on, and you're looking at the relationship between that key variable and some outcome or some set of outcomes. You certainly want to start with a linear form, but if you're focusing on one key variable, you want to take a pretty close look to make sure that whatever functional form, that linear relationship, let's say, accurately characterizes the results. And sometimes it does, and sometimes it doesn't. Sometimes you can go with a spline to capture it better. Sometimes you can go with a parabola. And that's what we'll be talking about next time. A lot of people use parabolic forms when they deal with growth models. Weight and growth models. We'll talk a bit about these, but they amount to a multi-level model where first level is an equation like test score A plus B1 age. All right, that should look familiar. That's what we started out with in the first lecture. We saw what how B1 was calculated, the sum of xi minus x bar times yi minus y bar all over the sum of xi minus x bar squared. But what often happens, and then level 2 is to explain the B1s with covariates. So you estimate this for every child. And then you take what you get as an estimate of B and then plug it into an equation. B1 is a function of family income, region, and so forth. Where quadratics come in, this is a linear equation, obviously, in a growth model that looks like this. There's a slope for every child showing linear growth, and that slope ends up being the dependent variable in the next level. A lot of these growth models don't just fit a linear model, they fit a quadratic model. And next time we'll talk about quadratics. Probably remember them from your algebra days. You're forcing a symmetric U shape to the functional form. But with growth models, you're getting both a parameter for the linear age effect and a parameter for the quadratic. So in this case, you still have an equation where you bring in the linear effect of age and try to explain that. But now you've got a quadratic term. To explain as well. So there'll usually be two sets of equations. Well, three really. There's always this first individual level equation, and the parameters from that you then try to explain with other covariates of interest. So, you know, like it or not, I have my problems with growth models, as I will talk about, but they're pretty widely used in education research. So it's good to understand them. And the heart of many growth models is a simple quadratic with time or age. So it's important to spend a little time with quadratics. And that's what we'll feature next week.